Okay, so we are in section 2.6 now, and we're going to talk about limits at infinity. And so we have an intuitive definition, which is going to be similar to the one we had for limits approaching a point in the domain. So it's a little bit different, but so if we have the limit as x goes to infinity of a function, if that is equal to some number L, that means that, so that is to say, the limit as x goes to infinity of f of x is equal to L if the function can be made arbitrarily close to L by making x sufficiently large. Okay. So this arbitrarily close, I'm not sure if I used this exact wording before, but I think I did say that I used the phrase like as close as we like, right? And this is just meaning the same thing. So as close as we would like, we can get to L just by making x sufficiently large. And then the corresponding limit as x goes to minus infinity is equal to L. It's basically the same thing. So if f of x can be made arbitrarily close to L by making x sufficiently, here we will want large and negative. So one thing, just to clarify, when I'm talking about large versus small, when we're talking about limits, I mean in absolute value. So I mean like the absolute value, which sort of gives you the size of the number, but not its sign, right? So when I say large and negative, I mean like a very large, say like negative 10,000, but negative, right? So you can think of taking like large numbers like that, but in the negative direction on the number line. Okay, so this is the part that tells us we're going, that x is going to minus infinity. And here, this is the part that tells us that x is going to positive infinity. Okay, so let's look at this example here. This is the graph of this function, and you can see, so limits to plus and minus infinity, they have to do with what's going on sort of at the ends of the graph. So it would be like here and here. And if we imagine, extending this graph all the way out, it looks like it would be getting closer and closer to this dotted line, which is the line y equals 1, right? Okay, so I'm going to write this out just so we can see the connection between the definition and the limit. So as x goes to infinity, I'll just write the symbol. And another way you can think about this is to say that x increases without bound. So it can be hard to kind of like wrap your mind around the idea of infinity. It is a pretty strange concept, but maybe increases without bound is more friendly as an idea. I don't know. So either way you want to think about it. As x goes to infinity, the function gets closer and closer to 1. So that means that the limit as x goes to infinity of this function is equal to 1. And similarly, on the other side, we have basically the same behavior because this function is symmetric about the y-axis, but as x tends to minus infinity or decreases without bound, the function gets closer and closer to 1. So that means that we can write the limit as x goes to minus infinity of f of x is equal to 1. Okay? And so the definition of a horizontal asymptote is just that, so y equals L is a horizontal asymptote of a function f if we have either the limit as x goes to infinity of f of x equals L or the limit as x goes to minus infinity of f of x equals L. We don't need both. We could have either one or the other, or we could have both. And in any of those cases, we have a horizontal asymptote. Okay? And just something to note is that here L should be a finite number, right? So we know that limits can be equal to infinity, but in this case, when I write this L, it's not going to be infinity. It's going to be a finite number. Okay, so let's look at some graphical examples. So here we have a function that oscillates up and down as we get as x gets larger, right? So I'm going to call this function g and this one h. So we can see that the function values are getting closer and closer to 0 as we move this way along the x-axis, so out towards infinity. And so the limit as x goes to infinity of g is equal to 0. And then similarly, we have the same behavior going on the other side of the graph. So as x goes to minus infinity, this limit is also 0. Now, notice that this function does bounce up and down, and it crosses that line y equals 0. Or maybe I should first say, so the horizontal asymptote will be y equals 0, right? So we got that both of those limits were equal to 0, so we have a horizontal asymptote at 0. And it's okay for the function to cross the horizontal asymptote. So I do have these two graphical examples, but I do also encourage you to look in the textbook. In this section, they have in the margin a bunch of just graphs that show horizontal asymptotes, like all the different ways that they might look, and that can be helpful if you're trying to get an idea of what these look like, right? Okay, so here we have another example. So notice that this is actually an exponential curve. So we know that exponential curves have this asymptote at 0. I think we mentioned that before, but now we have a way of writing this down and like a proper definition. So the limit as x goes to minus infinity of this function is equal to 0 because the graph gets closer and closer to 0 as we go out towards negative infinity. So we have a horizontal asymptote at 0. And notice we didn't have, so we only had it going one way, so going towards minus infinity, the function approaches 0, and that's all we need to say that there's a horizontal asymptote, right? So there. So they actually both have a horizontal asymptote at 0. Okay, so let's talk about some examples. So first of all, this function sine of x, we know what the graph of this function looks like, right? So it bounces up and down like this, and we know that this actually continues on. So this function looks like this all the way out to infinity. So it bounces between minus 1 and 1. So that means that it does not approach a single value. Or get close to a single value. So unlike in the previous example we had where this function is oscillating in the same way, but it's getting closer and closer each time it goes up and down, it gets a little bit closer to 0. Instead, sine of x stays the same distance, or it always travels the same distance between minus 1 and 1 and never gets closer to a single point or value. So that means that this limit as x goes to infinity, I guess we don't need the equals, so this does not exist. Okay. Okay, here we have the limit as x goes to infinity of 1 over x. So we could look at a table of values to get an idea of what's going on here. So if we have, let's say we take some values of x, like 1, 10, 100, 1,000, maybe 10,000, like that. And then we want to evaluate 1 over x at those points. So I'm going to write these as decimals to make it a little bit easier. So we get 0.01 and then 0.001, 0.0001, and we can see that this is getting progressively smaller as we take larger numbers, right? So as x gets larger, 1 over x gets smaller, meaning closer to 0. So this tends to 0. So we can write the limit as x goes to infinity of 1 over x equals 0. I should mention that while it is very helpful to create these tables and get an idea of what the function is doing by taking some test points, you can't always rely on this, especially if you have like a very strange function, which, you know, we can definitely come up with examples of functions that behave very strangely. But so one way of verifying that this is actually true is by looking at the graph, so that you just didn't pick, points that made it seem like this function was approaching a value that it wasn't. And so we know, or we can always graph it. 1 over x looks like this, right? So as we go out towards infinity, maybe I should draw it a little bit better than that. we can see that the function approaches 0 as we move out towards infinity. So it is actually the case that this limit is equal to 0. And we also have that the limit as x goes to minus infinity of 1 over x is equal to 0. Okay. Oh. Okay. Here we go. Okay, actually we can generalize this a little bit. So we get the same behavior. So in fact, if we have a number r greater than 0, and if this is a rational number, then we can also say that the limit as x goes to infinity of 1 over x to the r is equal to 0. Okay? So in particular, if you have an integer, a natural number, so greater than 0. Oh, wait. Okay. Sorry about that. Then you have that 1 over x to that power is going to be, so the limit as x goes to infinity is going to be 0. And we can also say, so in the other direction, we do have to make an exception. So if it is the case that x to the r is defined for x less than 0, then we can do the limit as x goes to minus infinity of 1 over x to the r. And that is also equal to 0. Okay, so one thing, so the reason why we have to do this is, why we have to make this statement in this way is because, for example, if we had r equals 1/2, then 1 over x to the r would be 1 over the square root of x, right? And that would not be defined for x less than 0. And this happens for a lot of values of r, actually, because if it's a fraction with an even denominator, we run into a problem. So this would not be defined, and that's why we have to be careful with our wording. Okay, but this fact is actually very useful, and we're going to be using it for, actually computing limits. So we use it quite a bit. Okay, so just to say something about this in general, if you're taking the limit of a rational function, so, or really any fraction, if the denominator blows up, so goes to infinity, so let me put that in there, to infinity, or actually minus infinity, so goes to plus or minus infinity, and the numerator stays fixed, then the limit will be 0. Okay, so this is sort of the opposite statement of what we said before, which was that, so as as we noted before, if the denominator blows up, or sorry, not if the denominator blows up, we did that case. If the denominator gets small, he tends to 0, then, and the numerator stays fixed, then the limit will be plus or minus infinity, right? So this is what we talked about before. And then we have sort of the reverse statement, which is when the denominator is getting big, then the whole fraction will get small. So this case that we talked about before is actually the trickier one because we have to worry about whether it is positive or negative. This one's a little bit easier to apply because the limit will just be 0 and it will always be 0. So no worrying about signs and stuff like that. Okay, I think I'm going to end it here and then we will talk more about, so we'll do some examples in the next video.